In 1835, a well-known French philosopher, Auguste Comte, stated that humans would never be able to understand the real nature of the stars, i.e. their chemical composition. But he was soon proved wrong, because luckily in the latter half of the 19th century, there was a sort of revolution in the astronomy field. Astronomers began to make use of two new techniques, spectroscopy and photography. We can say that was likely the birth of astrophysics. Together, spectroscopy and photography helped bring a new understanding of the cosmos, and for the first time, scientists could investigate what the universe was made of. They could understand how the sun was burning and what the sun was burning. This was a major turning point in the development of a newly born science, cosmology. Astronomers were able to record and document not only where the stars were, but what they were as well. But what's spectroscopy? And what's exactly astrophysics? Astrophysics is a science that uses methods and principles, or we could say the power of physics, with the aim of studying astronomical objects and phenomena. Of course, among the subjects studied are the sun, other stars, and galaxies. But astrophysics also studies extrasolar planets, the interstellar medium, and the cosmic microwave background. How can scientists study these objects? How is it done? Well, they study their emissions. In fact, every object has its own emission, which we can think of as the intrinsical energy of the object that produces a spectrum. Emissions from these objects are examined across all parts of the electromagnetic range, and the properties examined include luminosity, density, temperature, and chemical composition. Astrophysics is a very broad subject, and it applies concepts and methods from many disciplines of physics, including classical mechanics, electromagnetism, statistical mechanics, thermodynamics, quantum mechanics, relativity, nuclear and particle physics, and atomic and molecular physics. That's why one has to study a lot in order to become an astrophysicist. In practice, modern research often involves a huge amount of work in the realms of both theoretical and observational physics. Astrophysicists are trying to determine the properties of dark matter, dark energy, black holes, and other celestial bodies, and the origin and ultimate fate of the universe. Theoretical astrophysics also wonders how the solar system formed and evolved, and involves the study of stellar dynamics and evolution. We said that astrophysicists study the spectrum of celestial objects, but what exactly is a spectrum? All normal matter emits electromagnetic radiation when it has a temperature above absolute zero. The radiation represents a conversion of a body's internal energy into electromagnetic energy, and is therefore called thermal radiation. It is a spontaneous process of radiative distribution of entropy. Conversely, all normal matter absorbs electromagnetic radiation to some degree. An object that absorbs all radiation falling on it at all wavelengths is called a black body. When a black body is at a uniform temperature, its emission has a characteristic frequency distribution that depends on the temperature. Its emission is called black body radiation. The spectrum of a star is composed mainly of thermal radiation that produces a continuous spectrum. The star emits light over the entire electromagnetic spectrum from gamma rays to radio waves. However, stars do not emit the same amount of energy at all wavelengths. Nowadays, we are well aware of all these things, but at the end of the 19th century, physicists were unable to explain why the observed spectrum of blackbody radiation, which by then had been accurately measured, diverged significantly at higher frequencies from that predicted by existing theories. Blackbody radiation is the thermal electromagnetic radiation within or surrounding a body in thermodynamic equilibrium with its environment emitted by a black body, an idealized, opaque, non-reflective body. The concept of the black body is in fact an idealization, as perfect black bodies do not exist in nature. Graphite and lamp black with emissivities greater than 0.95, however, are good approximations to a black material. In 1900, Max Planck derived a formula for the observed spectrum of a black body. The Planckian function is a function of only the frequency of the radiation and the body's temperature. A typical Planckian function looks like this. Today we know stars can, in first approximation, be thought of as black bodies, but their observed spectrum is not an exact Planckian function. This is because, as we stressed before, Black bodies are an idealization, something that doesn't really exist in nature. Here's the observed flux for a star. As you can see, it looks pretty different from the Planckian function, and it seems there are some lines missing. What caused them? This was a difficult question to answer, but then at the end of the 19th century, scientists Kirchhoff and Bunsen entered the game, and nothing stayed the same. It's time to give a proper answer to our second question. What's spectroscopy? Spectroscopy is the study of the interaction between matter and electromagnetic radiation as a function of the wavelength or frequency of the radiation. In simpler terms, spectroscopy is the precise study of color as generalized from visible light to all bands of the electromagnetic spectrum. We could say that in 1859, Gustav Kirchhoff and Robert Bunsen gave birth to spectroscopy. Bunsen reported to a colleague that Kirchhoff had made a totally unexpected discovery. He had identified the cause of the dark lines seen in the solar spectra. When certain chemicals were heated in Bunsen's burner, characteristic bright lines appeared. In some cases, these were at exactly the same points in the spectrum as the solar spectrum dark lines. The bright lines were light coming from hot gas, whereas the dark line showed an absorption of light in the cooler gas above the sun's surface. The two scientists found that every chemical element produces a unique spectrum. This provides a sort of fingerprint which can confirm the presence of that chemical. Kirchhoff and Bunsen recognized that this could be a powerful tool for the determination of the chemical composition of the sun and stars. And they were right. Astronomers and astrophysicists couldn't live today without spectroscopic surveys. The types of spectroscopy can be distinguished by the nature of the interaction between the energy and the material. These interactions include 1. Absorption spectroscopy. Absorption occurs when energy from the radiative source is absorbed by the material. 2. Emission spectroscopy. Emission indicates that radiative energy is released by the material. Spectroscopy is so important that British astronomer and chemist Warren de la Rue in 1861 stated, "If we were to go to the sun and to bring some portions of it and analyze them in our laboratories, we could not examine them more accurately than we can by this new mode of spectrum analysis." Now that we know what spectroscopy is, we can understand better how astrophysicists study star positions, masses, velocities, and all the other physical features of celestial bodies. In fact, spectroscopy provides us with positions of stars and gas clouds. For example, with the help of spectroscopy, we can understand better the spatial distribution of stars in our galaxy. Also, using the so-called virial theorem, we can infer stellar masses and chemical abundances of elements with respect to hydrogen. And last but not least, we use spectroscopy to study velocities. How do we? Well, maybe you've already heard about redshift and blueshift. Redshift and blueshift describe how light shifts towards shorter or longer wavelengths as objects in space, such as stars or galaxies, move closer or farther away from us. When an object moves away from us, the light is shifted to the red end of the spectrum, as its wavelengths get longer. By the amount of redshift, blueshift, we can infer the radial velocity of the object with respect to us. Isn't it amazing? Studying colors equals studying the universe. What does an astrophysicist do? An astrophysicist may perform research on the planets, the stars, other galaxies, and objects in the universe. They take an in-depth knowledge of physics and apply it to astrological theories. An astrophysicist may have the following responsibilities: develop astrological theories and implement research techniques to test those theories. Keep up to date with the latest research in the industry. Contribute data and research to the field. Analyze and develop programs and tools to further assist astrological research. Facilitate scientific experiments to learn more about the universe. In order to become an astrophysicist, one has to study a lot of physics, math, and astronomy. We could say jokingly that an astrophysicist studies the same physics of a physician, pretty much the same math of a mathematician, plus astronomy stuff. What are the main purposes for a NASA astrophysicist? On NASA's website, we can read, NASA's goal in astrophysics is to discover how the universe works, explore how it began and evolved, and search for life on planets around other stars. 3 broad scientific questions emanate from these goals. How does the universe work? probe the origin and density of our universe, including the nature of black holes, dark energy, dark matter, and gravity. How did we get here? Explore the origin and evolution of the galaxies, stars, and planets that could make up our universe. Are we alone? Discover and study planets around other stars and explore whether they could harbor life. Now that we know what astrophysics is, we can ask ourselves, what's the difference between astronomy, astrophysics, and cosmology? Cosmology studies the universe as a whole and its phenomena at the largest scales, unlike astronomy, astrophysics, which study individual objects. And then astronomy is primarily concerned with observing and measuring the relative positions and paths, then giving explanations. On the other hand, astrophysics and cosmology try to explain the phenomenon observed. Usually, the students of astronomy focus on classical mechanics and optical methods to be able to observe celestial bodies and predict their positions in the sky. Astrophysicists concern general relativity and nuclear physics as two important roles to describe stars or galaxies. Cosmologists are interested in modern theories too, especially string theory, and they ask themselves why the universe was born and how. Humans spend thousands of years gazing at the night sky and wondering about the presence of life elsewhere. Could it be in our solar system? Could it be on some other blue planet around another star? Nobody ever knew, but such thoughts have found their expression in fiction, scientific missions, and religions worldwide. Pondering the rise of life on our planet was not only a philosopher's but also an ordinary people job. Creation myths have been fundamental to every civilization and culture and reflected the profound resonance of the question of our origins. What about today? Did we make some steps forward? Today, astronomers have pushed back our understanding of the origins of the universe to tiny fractions of microseconds of the Big Bang. However, we can't yet give any satisfying definition of life, nor yet point to the exact time and conditions when the organic matter first went from unanimated to animated, from non-living to living. It was about 50 years ago when humanity began to extend its presence into space, first with robots and then with humans. As this tentative expansion of our species into other worlds continues, basic questions remain unanswered about the long-term adaptation of living organisms to other environments. For example, we often think about Mars as our second possible home, but we do not know what the effect will be of living for years on Mars. In fact, the pull of gravity on Mars is about 1/3 that of Earth. Astrobiologists try to answer this type of question. Let's start by simply answering the question, what's astrobiology? As it's easy to imagine, astrobiology is the study of life in the universe. Do you think it is an easy task? Well, I'm sorry to disappoint you, but life in the universe is actually one of the hardest things we can study. But let's go back for a moment when the term astrobiology was invented. It was only in the 1950s space age that the term astrobiology was coined. It was used to define the study of the biological impact of space missions and to define the study of the search for extraterrestrial life. Later, famous scientist Carl Sagan brought astrobiology to the public and to the scientific community, and the field began to gain recognition. So nowadays, astrobiology is defined as the science that studies the origin, distribution, and evolution of life in the universe. And it takes several branches of science, biology, geology, astronomy, physics, chemistry, but also engineering and society, and brings them all together. Astrobiologists can work alone on particular scientific questions, but often astrobiologists from different scientific disciplines work together to examine complex questions that no one field can answer alone. When we think about life in other worlds, what we immediately start to imagine is little green men or maybe tall, intelligent species that invade our home Earth on their technologically advanced spaceships. But this is science fiction. Do you want to know what we really know about life in the universe? Well, if we want to speculate about life in other worlds, what could it be? One of the logical starting points, and maybe the only one, is to start by looking at our own planet. In fact, for now, the only known planet hosting life is Earth. You'd say this is pretty obvious, right? So what do astrobiologists do next? They use a method called the Great Analogy. In short terms, they use the knowledge that they have from life on Earth, how it originated and evolved. Then they try to understand how to extrapolate that knowledge to other environments in the universe, such as our solar system. That's why the understanding of the origin of life on Earth is the main key in order to give a push to astrobiology. The question now is, what do we know about life on Earth? We know that here on Earth, life emerged around 3.8 billion years ago, probably in the deep oceans. Why? Well, we know that back then the Earth was not the same as today. What do we mean? We mean that if you were here, you could have not been able to breathe, because there was no oxygen at all, and there was no ozone layer. This means that we had a lot of radiation, and it brings us to the conclusion that the first forms of life would have to be anaerobic. They would have to avoid radiation and grow up without oxygen. That's why we think it originated in deep oceans. There, the radiation isn't an issue. These are our first clues about what it takes for life to emerge: liquid water and organic molecules. What we think is that the oceans brought the molecules around, and eventually the right molecules met at the right time and at the right place. That's how astrobiologists think life emerged. Also, by looking at the different life forms we study every day, we realize that biodiversity is amazingly big. Every day we find a new variety of organisms that live in places that we thought no life could ever exist. They are called extremophiles. An extremophile, from Latin extremis, meaning extreme, and Greek philia, meaning love, is an organism with optimal growth in environmental conditions considered extreme in that it is challenging for a carbon-based life form, such as all known life on Earth, to survive. These organisms are dominants in the evolutionary history of the planet. Dating back to more than 40 million years ago, extremophiles have continued to thrive in the most extreme conditions, making them one of the most abundant life forms. These microorganisms can live at temperatures above 100 degrees Celsius. Also, they live in acid rivers or very salty lakes, and they help us set the limits of life. Since one of the most extreme environments is actually space, astrobiologists ask themselves, can life survive in space? That's why they have done a lot of experiments in situ. They actually have sent bacteria and other microorganisms to space, put them on the outside of the International Space Station where they are exposed to the real space vacuum and the real space radiation. So they stood there for months, and what they found is that many of them actually survived. This is a sort of a revelation because it makes us wonder where else in the universe can life survive. So the first place we actually look, of course, is our own solar system. We begin by looking at the moon. We went there, there is no life there, but then we focus on other things. Before finding out what we found about life in our solar system, be sure to like or dislike the video so that we can continue to improve and make these videos better for you, the viewer. Plus, be sure to subscribe to the channel by clicking the bell so that you don't miss any of our weekly videos. If you'd like to help improve the quality of our content, please check us out on Patreon. We would like to say a big thank you to all those who show their support. Europa, Jupiter's moon. Did you know that the surface of Europa is made of water ice? Many scientists think that beneath the frozen surface is a layer of liquid water, literally an ocean, which is prevented from freezing by the heat from flexing. How do we know it? Evidence for this ocean includes geysers erupting through cracks in the surface ice, a weak magnetic field, and chaotic terrain on the surface, which could have been deformed by ocean currents swirling beneath. At the bottom of this ocean world, it is conceivable that we might find hydrothermal vents and ocean floor volcanoes. On Earth, such features often support very rich and diverse ecosystems. Could therefore Europa host or have hosted life? Titan, Saturn's moon. Titan is the only moon in the solar system with a substantial atmosphere. The atmosphere consists mostly of nitrogen, which is an important chemical element used in the construction of proteins in all known forms of life. Recently, radar observations have detected the presence of rivers and lakes of liquid methane and ethane, and possibly the presence of cryovolcanoes. Cryovolcanoes are volcanoes that erupt liquid water rather than lava. This suggests that Titan, like Europa, has a subsurface reserve of liquid water. Although it's distanced from the sun, it is very cold on Titan for liquid water, The bountiful chemicals available on Titan have raised speculation that life forms, potentially with fundamentally different chemistry from terrestrial organisms, could exist there. Mars. Mars is one of the most Earth-like worlds in the solar system. It has a 24.5-hour day, polar ice caps that expand and contract with the seasons, and a large array of surface features that were sculpted by water during the planet's history. Scientists detected the presence of a lake beneath the southern polar ice cap, which makes Mars a very interesting candidate for life. They also found methane. This is amazing because it could be produced by biological processes, even though the actual source for Mars's methane is not yet known. We just have to keep hoping and bringing information from the Martian soil, maybe with the fantastic help of perseverance and ingenuity. As one can imagine, while astrobiology is a relatively young field, it has a secure and promising future. Astrobiology research has a significant impact on how agencies such as NASA and the European Space Agency plan for current and future space missions. Many recent missions were launched with the aim of exploring worlds in our own solar system and find signs of past, present, or precursors of life, including Mars. One of the most famous missions was the Cassini mission, which gave us a better understanding of Saturn and its moons, such as Titan. Today we are waiting for the launch of the James Webb Space Telescope, which will allow us to begin searching for habitable planets outside our solar system. Communicating the discoveries and excitement of astrobiology has been understood as a fundamental requirement since the early development of the field. Meeting this objective has taken various forms. One element was a common form embodied in the Astrobiology Science Conference held biannually that today attracts over 800 scientists from over 30 fields. With meetings in 2000, 2002, 2004, and 2006 that have continued to grow in attendance, the conference remains a forum where scientists are encouraged to push the boundaries. What about the future of astrobiology? On NASA's website, we can read, "The first decade of astrobiology has laid significant groundwork for the understanding of the genesis and evolution of life in the universe. Fieldwork has provided fossils, organisms, and ecosystems that have all led to significant insight into the early Earth, possible models for origins, and a huge expansion of the recognized environmental limits of life. Laboratory work, coupled with astronomical observation, has added another significant piece of the puzzle and continues to provide clues and refine models. Missions are just beginning to take astrobiology to entirely new levels of understanding. Given the timeless fascination with questions of the origins and prevalence of life, astrobiology will endure long into the future.